So this is a tutorial for example 7-1 of McCain's book for the course of reservoir fluid properties at St. Francis University. This example is about recombination of compositions in order to get the original composition at the reservoir for a wet gas sample. So what we have separator gas composition, stock tank compositions, gas oil ratio at separator, and a stock tank and oil density. So whatever given data are shown in yellow color, and so we have the components C1 to C7 plus, composition of gas as separator, composition of gas at the stock tank, and composition of liquid at the stock tank. We have gas oil ratio at separator, gas oil ratio at stock tank, and also we have the APR degree, which is you could calculate the oil density. So, and also we have standard conditions, temperature and pressure at the standard condition. I'm going to talk about why we need that. So what we're going to do here is, first of all, to convert gas and liquid at separator and stock tank to moles, and using a material balance, mole material balance, we could basically calculate the fraction of vapor and liquid as separator and fraction of vapor and liquid at stock tank. And then using those values and using the composition, we could reconstruct the composition of liquid at the separator, and then using the composition of liquid and fraction of liquid and fraction of vapor and composition of gas as separator, create the original composition of the wet gas inside the reservoir. As you know, wet gas has single phase, is at a single phase inside the reservoir, but when it comes to the surface, we have liquid and gas. Therefore, we have two phase. To start, we have to calculate the molecular weight of stock tank oil, which is very simple using these mixing rules. So I already have the molecular weight of each component, and then since we have the composition of liquid in the at the stock tank, it should be really easy. I'm sorry, this is composition of liquid multiplied by the molecular weight for each component, and drag it down. And also what I'm interested is summation of these guys. So I use the summation function, and this gives me 100.93 pound per pound mole for this mixture. Okay, so the next step is to calculate the number of moles of separator gas produced per barrel of stock tank oil. So if I have one stock tank barrel of oil, I will have 69,551 standard cubic feet. But I would like to convert this to pound moles. In order to convert the SCF to pound moles, basically we use the molar volume. And we make an assumption here. The assumption is that at the standard conditions, we have ideal gas behavior. And using that, we could calculate the molar volume based on the ideal gas law, which is RT over P if we have the standard conditions. Temperature of 60 degrees of Fahrenheit, pressure of 40.65, and we have the R value. So that will give us 380.71, which is a universal value for if we have ideal gas behavior. So remember, this is molar volume, and the unit is SCF per pound mole. Therefore, you could convert the GOR value to pound mole divided by SCB. So that means per 1 SCB of oil will have how many moles? That would be this divided by this value. The next step is doing the same thing for the gas produced at stock tank. So number of moles of stock tank gas. So that would be the similar way. We have GOR divided by this. So this I will just copy this and I will have this. Okay. So I have number of moles of gas as separator, number of moles of gas as stock tank per production of 1 SCB. However, next step, I would like to calculate the number of moles of 1 barrel of stock tank, 1 SCB. In order to do that, I use the density. And since I have the molecular weight, I create the molar density. And then finally, I will make a unit conversion. The molar density has a unit of pound mole per cubic feet, but I'm interested in barrel because the unit of stock tank volume is barrel, so I will eventually convert it to pound mole per stock tank barrel. So to start with that, I have the API, and using the formula of API, which is 14.5 divided by specific gravity minus 131.5, I calculate the specific gravity of oil. I have done this before, so I will just copy paste it. So oil specific gravity using the same formula that I showed you here, I will calculate it. And since I have water density at the standard condition, I could calculate the oil density, pound per cubic feet. Okay, and that would be water density multiplied by specific gravity. Okay, however, I want to make the molar density. In order to create the molar density, which is pound moles divided by cubic feet, I use the regular density divided by the molecular weight of stock tank oil. Okay, and finally, I would like to convert the cubic feet to barrel because I'm dealing with a stock tank barrel. So I do the same thing. The only difference is this is barrel. The unit conversion from barrel to cubic feet is 5.615. So this would be basically this multiplied by this. Oops. Okay. So I will have 2.62. I'm going to change the color. This is number of moles per 1 SCB oil in a stock tank. So far I have number of moles of the gas at stock tank, number of oil of gas at separator, and number of moles of oil in stock tank and per 1 SCB production. To create a vapor fraction is very easy since we're dealing with the moles. Basically, vapor fraction at separator would be the number of moles at separator divided by the total number of moles, which would include the separator gas plus stock tank gas plus the stock tank oil. And the liquid fraction basically would be 1 minus the vapor fraction. Now if I convert it to percentage, just giving me the percentage value. For vapor and liquid fractions at stock tank, I have the stock tank vapor number of moles divided by the total number of moles at the stock tank. And again, this is per unit of 1 barrel of stock tank. And for liquid would be 1 minus the vapor fraction, or would be the number of moles of liquid divided by total number of moles at the stock tank. Okay, and the summation of these two should be 1. So let me try. Okay, so same thing for separator. Summation of these two should be 1. Alright, so far we have the fractions of liquid and gas. The next step is calculate the original composition of wet gas inside the reservoir. However, to do that we need the composition of the liquid at separator condition. Composition of liquid at separator condition would be fraction of vapor multiplied by the composition of gas at the stock tank plus the fraction of liquid, or 1 minus the fraction of liquid at the stock tank multiplied by the fraction of the composition of liquid, because basically the liquid will be summation of the gas plus liquid. The liquid at separator would be summation of the gas at the stock tank plus the liquid at the stock tank. So it's pretty easy. So here I already have written here. So I have composition of oil multiplied by vapor liquid fraction. I want to make this constant, so plus composition of gas multiplied by the fraction of gas at the stock tank, and I'm going to make this constant so it's not changing, and I will drag this down for all of them, and the summation of this, let's make it a little bit beautiful. Okay, and okay, this is good enough, and summation of this should be equal to 1. Sum this should be 1. The next step, calculating Zi, the original, and I will recombine the composition at separator and composition of gas at separator using the fraction of liquid and vapor at separator. So that would be composition of liquid multiplied by fraction of liquid. I'm going to make this constant, putting dollar sign around the cell, plus the Y value at separator multiplied by the fraction of liquid, fraction of vapor. Okay, and then again I will drag this down, and let me copy the format of cells here. Okay, and also the summation should be 1, which is okay. So quick recap, using the composition of gas at separator, composition of gas and liquid at the stock tank, having the gas-oil ratio at separator and stock tank, and the density of oil at the stock tank, we are able to calculate the number of moles per 1 SCB at separator condition and the stock tank condition, and calculate the vapor fraction and liquid fraction at separator and the stock tank, and basically through that, using those values to calculate the composition of liquid at separator, and eventually the composition of wet gas inside the reservoir. The Z here is the global